Hi, I'm Stephen Buescher, and I'm part of the team behind the AVL Simulation Suite. It's my pleasure today to introduce you to our latest release, 2026 R1. Let's take a look together at some of the highlights and new features in this release. Data-driven models are becoming increasingly important as a complement to classical physics-based simulation, especially when modeling complex system behavior. CRUISE M has supported this with built-in matrix operations in the compiled function component, enabling efficient implementation of custom neural network evaluators. With this release, CRUISE M introduces a more streamlined and generalized approach for integrating machine learning models. The new ONNX component based on the Open Neural Network Exchange standard. This component removes the need for manual coding or configuring a compiled function. You can now directly import ONNX models into CRUISE M with just an ONNX file. The ONNX component is available in the component library. Any model trained in an ONNX compatible tool, such as scikit-learn, PyTorch, MATLAB, or TensorFlow, can be imported. CRUISE M automatically detects the number and type of input and output channels, making it easy to connect the model to the rest of your CRUISE M system. Here, we're looking at the installation example, CO3021 Neural Network. Its setup is divided into three parts: input preparation, input monitoring, and output monitoring. Two random inputs, x1 and x2, are generated and transformed into a 12-element input tensor that matches the trained model's expected format. The ONNX component then evaluates this tensor and produces a single output value between 0 and 1. A conditional filter uses this output to selectively pass or reject data, creating distinct regions in a 2D visualization. In this particular example, the ONNX model was trained to reproduce the CRUISE M logo, which becomes visible when the simulation is running. In the online monitoring, you can see how the numerical variation of the inputs leads to changes in the output distribution and the 2D visualization, gradually converging into the final image. In the results, you can see the final image, along with the input tensor and the class distribution. Modern lithium-ion batteries often feature blends of different electrode materials to take advantage of individual material characteristics on energy density, safety, and durability. CRUISE M's electrochemical battery allows you to simulate such blends with a unique heterogeneous electrode approach. With this version, the performance of the heterogeneous model is demonstrated on the example of a commercial 26,700 cylindrical cell with an LMFP NMC blended cathode. The installation example you see on your screen features fully parametrized models, including all experimental reference data on the results pages. In this example, we are showcasing the performance of both the heterogeneous modeling approach and the homogeneous electrode modeling approach. If we open the battery properties, we can define two materials, LMFP and NMC for the cathode, which means that in this case, both materials are considered separately. This is the heterogeneous modeling approach. If we open the battery properties, we can also define the LMFP and NMC as a single material for the whole cathode, which means that the LMFP NMC is considered as a single affected cathode material. This is the homogeneous modeling approach. Both the heterogeneous and homogeneous models are parametrized on experimental data. The two modeling depths are validated in charge-discharge simulations at different C rates and temperatures to illustrate the potential and limitations of the different modeling depths. The advantages of the heterogeneous approach become apparent at low temperature and/or high loads due to the sluggish LMFP diffusion and the rapid decline in NMC kinetics with decreasing temperature. Allowing material-dependent depth of discharge is essential for understanding temperature-dependent capacity reduction caused by diffusion limitations. The result pages show voltage and temperature response for various C rates at 10, 25, and 40 degrees Celsius for both heterogeneous and homogeneous electrode models and compare them to measurements. Simulation plays a vital role in assessing thermal runaway propagation. It allows you to save time and cost for demanding experimental campaigns. In this example, we will showcase battery venting on the battery module. Battery venting is a critical safety feature designed to release gases, pressure, or heat from battery cell during abnormal conditions like overcharging, overheating, or short-circuiting. It prevents pressure buildup that could lead to cell swelling, fire, or explosion, acting as a controlled release mechanism. Furthermore, if we select thermal runaway, we have two options. By clicking on the battery module and on thermal runaway, we can see heat release and venting. Heat release defines the energy output and at what temperature it will start. Venting follows the same principle, but instead of defining energy output, we define whether it is time or battery temperature dependent. On the battery side, the module consists of 3 stack elements, and in each stack element there are 4 batteries. Altogether, there are 12 batteries. To cause the first battery to ignite spontaneously, 50 kilowatts of energy are instantaneously injected into it, causing a thermal runaway. If we check the results, we can clearly see that the venting procedure has started as we defined it in the properties, and that it is releasing excessive heat to prevent pressure buildup. The fuel cell and electrolyzer parameterization wizards have been expanded with the feature that allows the user to examine how the different fitting parameters affect the quality of the fit. This new feature is available in the wizard with the new setting Evaluate Fisher Information Matrix, accessible under the Optimization Settings section. Here, we are fetching the optimal fit which has been already obtained by a previous fitting. After the best fit has been obtained, at the end of the fitting procedure, the wizard will evaluate the Fisher Information Matrix. The Fisher Information Matrix will be written into the text log, but it is also possible to access it in a nice and graphically easy to read form in the graphical report, from where the figure can be saved, and where it is easy to examine the variances and covariances of the different parameters. This allows us to see which parameters do not affect the quality of the fit, and which parameters are covariate between each other, meaning that changing one will also affect the quality of the fit of the other. The head block compound feature is designed to integrate seamlessly with 0D or 1D thermodynamic engine models. It represents a finite element-based thermal structure that includes the cylinder head, engine block, piston, liner, as well as the intake and exhaust ports. This thermal model is automatically generated using a template-based approach, relying on simplified geometric inputs rather than detailed CAD data, which significantly streamlines the setup process. Once properly connected to the engine model, the simulation can start. It will take some time, so this part of the process is sped up. The user is provided comprehensive results in the post-processing environment. These results can be analyzed through curve data or via 3D visualizations and animations. Additionally, the system supports the coupling of multiple components, enabling the simulation of multi-cylinder engine configurations. This model represents a system-level simulation of an internal combustion engine, where the intake system is modeled using 1D pipes and a plenum. In the new release, it is now possible to replace specific parts of the system with a 3D CFD model. In Fire M, the CAD geometry must be prepared, meshed, and assigned appropriate boundary conditions for coupling with the 1D model. For co-simulation, an FMI is created in Fire M and then imported into the CRUISE M model. Within the subsystem mask, the user can configure co-simulation settings and load the corresponding Fire M FMU. Here, CFD results for EGR concentration are shown alongside the mass flow entering individual cylinders. The main advantage of this approach is improved prediction of air charge composition using the Fire M model compared to simplified 1D gas exchange methods. If you would like to find out more about any of the features shown in the video today, or any of the other highlights from the release, you can check our website avl.com or look on our simulation blog. See you at the next release.